Hello, this is Mrs. Sargent, and today we're going to start talking about kinetics. This is from chapter 12 in your textbook. So just a little bit about kinetics. Although we can know a lot of things from the chemical reaction, including the reactants and the expected products, the stoichiometry and the energy, we must understand that the rate of the reaction to truly grasp what's occurring. So the rate of the reaction is referring to how fast or slow the reaction is occurring. So although graphite can be compressed into a diamond, the reaction is so slow that we cannot view this in our lifetime. Therefore, we must choose to examine only those reactions that occur at a reasonable rate. So, chemical kinetics. Just a little bit of review. Thermodynamics is going to tell us if a reaction can occur. Remember, we talked about if the reaction is favorable or unfavorable, if it is spontaneous or non-spontaneous. So that's what thermodynamics tells us. Kinetics tells us how quickly the reaction occurs. Some reactions that are thermodynamically feasible or favorable are kinetically so slow as to be imperceptible. So we cannot view these in our lifetime, kind of like the diamond that we talked about. So here is an example. A carbon diamond with oxygen produces carbon dioxide. This is a very, very slow reaction. So slow that a lot of women have diamonds. They're not changing into gas in front of our eyes. So it is a very, very slow reaction. However, if we have hydrogen ions and hydroxide ions, combining those are instantaneously going to form gas. Both of these reactions are favorable. As you can see, delta G is negative, but we would only be able to view the water formation one. So in 12.1, it starts off talking about reaction rates. Reaction rate is the change in concentration of a reaction or product per unit of time. So here's a graph showing the reactant is decreasing and the products are increasing. We will write the concentration in a moles per liter as A in brackets, where A is the substance. So you would just put what is the concentration, like is it 4 molar? You would put that in what the substance is in the brackets. If the rate expression involves a reactant, the rate equals the negative change in concentration over the change in time. It is negative because the concentration, that's what these brackets are going to refer to, is concentration. So anytime you see brackets, just read that as the concentration. So the reason why the rate is negative is because A is our reactant and the concentration of your reactant is going to decrease as the reaction progresses. The above gives an average rate. So this equation here is going to give us the average rate for the reaction. Now, why does it matter that it is an average rate? Well, to get an instantaneous rate, we can compute the slope of a line tangent to the curve at that point. So rate is equal to the negative slope of the tangent line. You saw that in the graph here we had these curves, and then you have this tangent line going there. Also in this picture we have this curve showing the decrease of the reactant over time, and the tangent is showing us the rate. So we use initial rates. The rate of a reaction is not constant, but it changes with time because the concentrations changes with time. So this is why it's an average. We will only work with reaction rates that are initial rates, meaning that we're only looking at the reaction going in the forward direction. We're not going to look at the reaction going in the reverse direction. So this graph is showing the decay of nitrogen dioxide. So one of the things it tells you on your notes is to label the line corresponding to the reactant or product from the above reaction. So since nitrogen dioxide is our reactant, that is the only thing that is not going to be at 0 because that's the only thing that we're starting with. So this is going to be our NO2 curve. And then we have two products. And we have two lines here that are showing the products. Now, if you notice in the equation, we have 2 moles of nitrogen monoxide and only 1 mole of O2. So when we're trying to determine which curve is going to be which product, since this looks like it's almost twice as much as this bottom curve, this is going to be NO, and this is going to be O2. So there are some key things to note. As NO2 decreases in concentration, the concentration of each product increases. So we see the decrease of NO2, and in that same amount of time, we see an increase in both of our products. The concentration decrease of NO2 is equal to the concentration increase of NO, but it's twice that of O2. So this is reflected by the mole ratio. So then we get into 12.2, and it's rate laws and introduction. So rate laws can express how quickly reactant is consumed or the rate at which the product is produced, whichever way you want to think about that. If you're thinking about the reactant being consumed by the reaction, so it looks like it's disappearing, or if you want to think about how quickly the product is being produced. So in this chapter, however, we will focus on the consumption of the reactants. We will make an assumption that only the forward reaction is going to be the reaction that is occurring. Now, we haven't talked a whole lot about reverse reactions, but that is a possibility. So just like we've done everything, we're going to think about our reactions going in one direction only. So the differential rate law, or the rate equation, is a rate law that expresses how the rate depends on concentration. So we have a generic reaction here. You have A and B as reactants, and you have G and H as products. So the rate law, or rate equation for this reactant, is going to be rate equals K times the concentration of A raised to the power of M times the concentration of B raised to the power of N. So remember that because A and B are in brackets, that's representing concentration, so those represent molarities. The M and the N, those are your exponents. So let's talk about how you get those exponents. So I have that same rate law over here. The exponents are positive or negative integers, or they can also be fractions. Usually positive integers or small whole numbers. K is equal to the rate constant, and the value for K depends on your type of reaction. It also depends on the temperature of the reaction, or do you have a catalyst present in your reaction. The faster the reaction, the larger the value for K. The exponents determine the order. So what does order mean here? This means how much effect does this substance have on the rate? So the exponents determine the order of the reactants, and then the sum, so adding your exponents together, is going to determine the order of the entire reaction. So the rate law, K equals the concentration of A times the concentration of B squared. It is first order with respect to A, but it is second order in respect to B, meaning that it is third order overall. So the units of K can be calculated by reaction orders and units of concentration and rate. In order to find the units for the rate constant, for example, if the rate is in moles per liter times second, in the above rate law, we can find unit for K as follows. So here I just plugged in what are the units, and then simplified it down here. There is a shortcut in determining the units of K, and it is as follows. K equals the liters raised to a power divided by moles raised to a power times time. So the value of X will be one less than the overall order of the reaction. So if the reaction is third order, K equals liters squared divided by moles squared times time. If it is second order, K equals liters over moles times time. And if it is first order, K equals 1 over time. So it is something kind of just committing these to memory, making yourself a cheat sheet to while you're working on problems, to have those readily available for you. So there will be another video that we will actually look at determining the form of the rate law and looking at some actual equations. If you have any questions, please don't hesitate to ask. Thanks. Have a great day.